Hey everyone, welcome back to AI Unplugged. I'm your host, Travis Freisinger. In our last episode, we explored the role of conversational interfaces in AI product development. Today, we're delving into the foundations of modern AI, vector databases, and embeddings, plus a few extra tidbits. In this episode, we'll unpack how embeddings represent data in high dimensional space, enabling AI systems to understand context and similarity. We'll also explore vector databases, what they are, how they work, and why they're essential for storing and retrieving embeddings efficiently. Plus, we'll compare vector search with traditional lexical search and full text search systems like Elasticsearch and any kind of SQL database full text capability, while discussing the role of graph databases like Neo4j in AI systems and how these technologies differ and at the same time complement each other. It's all about layers, people. So let's get comfortable as we journey into the core technologies that make modern AI systems more contextual, personalized, and scalable. Let's start with embeddings. And if you're new to this concept, think of embeddings as a way to represent data, like words, images, or even user behavior, in a numerical form that captures its meaning or context. But what does it actually mean? Now imagine you're at a party trying to introduce two friends you've never met before. You might say, hey, you both love hiking and jazz. You're identifying commonalities to establish a connection. Embeddings do something similar, but in a mathematical way. They capture the essence of data points and place them in high dimensional space where similar items are closer together. Obviously, there's nuance. Talking big picture. For example, in natural language processing, words with similar meanings end up near each other in this space. The word king might be close to the word queen. Royal or monarch. This spatial relationship allows AI models to understand the context, perform similarity searches, and make nuanced predictions. So embeddings aren't limited to words. They can represent images, products, user preferences, you name it. So let's look at an example. Let's say we've got an image search engine, and each image is converted into an embedding that captures its visual features. So when a user uploads a photo, the system generates an embedding for that image and searches for other images with similar embeddings, effectively finding visually similar images even if they have different metadata or tags. So it's an extra layer on top of your typical full text or lexical type analysis that, if you've been around for a while, you'd be used to. Like in a recommendation system, embeddings can capture user behavior, product features, enable the system to suggest items you might like based on your past interactions. I think a more grounded way to look at this is to think about how Google search has evolved. It's come a long way over the years. So, you say you search for something like best laptops. Google might show you results for affordable gaming laptops or laptops for students or some variety of terms around that. This is because Google's modern search system, not the old school stuff back in the day, uses models like BERT and MUM for embeddings and natural language processing to better understand the intent behind the search, not just the keywords. But, like all good technologies out there, Google doesn't rely solely on just embeddings or vector search. It uses a layered approach, combining traditional keyword based ranking systems, where it started, with semantic techniques. Keyword based systems still excel at certain tasks like structured data queries and exact matches, but embeddings allow for richer, context aware searches that capture the meaning behind a user's query. And this hybrid approach allows Google to balance the precision and deeper understanding of the query, ensuring relevant results across the broad spectrum of searches. It's not as good as it used to be, but maybe I'm biased with the way ChatGPT works these days. I find myself going there a lot less than I used to. Might be the ads, might be a variety of things, but it's neat to think about how it started back as a real basic kind of search engine on text and how it's evolved to be quite a multi-layered product out there. So where are you going to see some personalizations around embeddings? Well, Siri or Alexa, they're going to use embeddings to understand what you mean when you give a command, allowing them to respond appropriately even if your wording isn't precise. It's able to kind of find it in the vector space as something similar. Oh, I get it, map it to that, and go. So how are the embeddings created, right? Well, they're typically generated by a neural network trained on large data sets. Surprise, neural networks. So for text, you've got models like Word2Vec, Glovey, or more transformer-based models like BERT that take words or sentences and produce vectors, effectively an array of numbers that encapsulate their meaning. So let's consider an AI system designed to recommend movies. It might use embeddings to represent both movies and users. If you watch several action films, your embeddings will be located near those movies in the vector space. The system can then recommend other action movies that are nearby, even if you've never heard of them before. So embeddings are powerful because they convert complex, unstructured data, key here, unstructured, into a form that machines can easily process. Traditionally, unstructured data has been a real pain if you've tried to put it through more text-based analysis mechanisms. They allow AI systems to perform mathematical operations on concepts. So as a famous example of king minus man plus woman equals a vector close to queen. This example shows how embeddings capture semantic meaning in a relationship in a way that's computationally useful. Understanding embeddings is crucial for AI engineers because it enables them to build systems that are more intuitive and responsive to user needs. Remember last week's episode, really honing in on the user experience side. Tools aren't just for fun, right? They're not just for the nerds of the world. We're really trying to build systems that help people. So whether it's enhancing search functionality, improving recommendations, or enabling complex natural language understanding, embeddings are at the heart of these capabilities. So they're not new. They've been around. Just this resurgence of AI, this generative AI wave that's kind of bringing them to being a hot technology. So the next time you're impressed by how accurately Spotify suggests a new song or Netflix seems to know your taste in movies, remember that embeddings are working behind the scenes to make that possible. Now, of course, embeddings are just one piece of the puzzle, right? It's about layers, people. Platforms like Spotify and Netflix also use techniques such as collaborative filtering, user ratings, and metadata to enhance the recommendation algorithm. Together, these methods help deliver highly personalized suggestions by capturing both the content, characteristics, and user preferences in a multi-dimensional space. So, we've touched on Google. So let's talk a little bit more about search. It's one of the most fundamental functionalities in technology, I would say. Spent a good part of my career dealing with search or search-related things. Done a lot of Elasticsearch work, been working with it, since it came out, basically. Anyway, we traditionally relied on keyword-based or lexical search systems like Elasticsearch to find information. These systems index data based on exact word matches, term frequency, and other factors. So, say, for example, you search the word apple, you'll get documents containing the word apple. It's also a concept called stemming. So if apple or apples came through, it would stem it back to the root apple. Lexical search engines are powerful, and they've been the backbone of search technologies for years, absolute years. Way before Elastic, there was Solr and other tech as well in this space. They excel at handling structured queries and can scale to handle massive amounts of textual data. Absolutely. Tools like Elasticsearch allow for complex querying, filtering, and aggregation, making them indispensable for many applications. I cannot reiterate that statement enough. They're indispensable for many applications. However, lexical search has its limitations. Surprise! It doesn't understand context or semantics. So if you search for smartphone, you might miss results that contain the term mobile, phone, or cell phone, even though they're related terms. So, in this case, synonyms, misspellings, conceptual similarities can trip up a pure lexical system. So before we move on from lexical search, it's also worth mentioning that some systems like particularly just about any variety of SQL database, also offer for full text search as a step before implementing more complex engines like Elasticsearch. Definitely been there, started off on client projects. Oh, we just want the SQL full text. Show them a little taste of what Elastic can do. Can you swap that out, please? Sure, no problem. We built it modularly. We've used clean architecture, built our own frameworks around it, and it worked. True story. Full text search in SQL supports capabilities such as ranking results based on relevance, tokenization of text into searchable units, and in some cases, basic synonym handling. For example, SQL Server or Postgres SQL, Postgres and SQL Server, the only two decent ones out there. Nothing against MySQL. It's got its time and place. Full text search indexes are created to enable more efficient querying of unstructured data. Throw some JSON blobs at them as well. And kind of figure it out. These systems can handle pluralization, stemming, run without, running stem to run, apples to apple. And in some cases, Thesaurus features to deal with common synonyms, like I was saying. While not as advanced as Elasticsearch or vector search, these techniques help minimize the issue of synonym and variation in phrasing. So full text is trying to catch up. I wouldn't use full text and Elastic. I would just say use Elastic based on my experiences. But situations do vary. Additionally, there are extensions and plugins that further enhance the full-text search in SQL databases, allowing them to correct minor typos or suggest alternatives. However, it's still largely limited to comparing what vector search achieves in terms of semantic understanding. So you got to go vector to get the semantics, really. In practice, I was saying many teams start with SQL for its simplicity. Integration to existing systems, they'll generally move on to Elastic and then potentially vector or vector as their search needs become more complex. So I guess what I'm saying is if you haven't made that jump and maybe you're still at full text, maybe you've done some Elastic, it's not hard to put some vector stuff in next to it, right? It's not hard to wedge a little AI type tech next to things and start to see the value it can add. So for AI engineers, understanding where full-text search fits can be a key part of building efficient, scalable solutions. Full-text, lexical, not all about just the vectors, people. So this is where vectors come into play, right? So we've looked at full-text, we've looked at lexical, maybe we hit some limits on what we can do, maybe we just want to see if there's an ability to kind of expand the fidelity of what we have. Let's put some vectors down. They can retrieve results based on semantic similarity. So a search for smartphone would surface documents containing mobile or cell phone, providing a more comprehensive set of results. So let's look at an example, right? So let's say we're running a support center and customers often ask, how do I change my password? A lexical search system, the knowledge article is based on a title called Resetting Your Login Credentials. So let's say we've got a knowledge base. That's the title of the article. Now the query might not match that article due to the difference in wording. A vector search system understanding that change password and reset login credentials are semantically similar would successfully retrieve the relevant article. Obviously, this is excluding tagging or some of the other things that you could do to help hint in the non-vector search world, but you get the point. Vector search represents a paradigm shift from keyword matching to semantic understanding, and it really is a paradigm shift. I've spent a lot of my career more at the keyword level, just starting to really feel comfortable in the semantic world. It enhances the search experience by capturing the intent behind queries, leading to more relevant and satisfying results. But does this mean that lexical search is obsolete? Not at all. In fact, many modern systems use a hybrid, layers, combining the strengths of both lexical and vector search. If you're just doing systems with vector search in, some LLM, are you really building AI systems, or are you just having a bit of fun? Putting it out there. Lexical search is perfect for precise filtering, Boolean queries, and handling structured data. Vector search shines in understanding unstructured data and semantic relationships. You need both. For AI engineers, understanding the difference and synergies between these two types of search is essential. Integrating vector search capabilities into existing systems can greatly enhance their effectiveness. For instance, Elasticsearch now offers plugins and features that support vector search. You can put the two next to each other. I've played with a bit. It was a real small example to kind of see. That's cool. It's nice to be able to have one system, right? Provided you got an Elasticsearch instance hosted somewhere if you're actually going to push this out. I guess otherwise just Dockerize it, right? Allowing for a seamless blend of traditional and modern search methodologies. When we used to build data representations, we often combine multiple technologies to achieve our goals. So back in the day, without vector search. So for example, we had Elasticsearch for fast, scalable keyword search. We had Oracle database that stored the structured data, and we were using a graph database known as Neo4j to model the complex relationships, effectively using tuples, model the relationships between two entities. Like a lecturer has students and how that plays out. And now it was all the same data. It was a very complex data engineering system, but it worked. It was even harder to visualize that and provide an interface in, but we figured it all out. This is like 10 years ago I was building this kind of stuff. So nothing in this technology stack is new. I think the newest piece of the technology stack here is the idea of embeddings and semantic. But like it's already established in other things. So what's the key takeaway? It's that vector search doesn't replace lexical search, but complements it. By combining both, we can build robust systems that handle a wide range of queries efficiently and effectively. So I've briefly touched on vector databases, but before I kind of journey down that road a bit further, let's take a moment to clarify the differences between embedding models and LLMs. Because they're different things, even though they're neural networks, and they're both important in this AI engineer space. Now, while both are foundational to modern AI, they serve very different purposes and fit into very different stages of the AI software development process. So first, let's talk about embedding models. Their job is to convert data, whether it be text, images, or other formats, into high-dimensional vectors or embeddings, as we discussed earlier. The process encodes the meaning or context of that data into numerical form that machines can easily work with. Embedding models are typically focused on generating these fixed representations of data. They're embedding models, right? Examples of popular embedding models include Word2Vec, BERT, SentenceBERT. These models focus primarily on capturing the relationship and the context, making them efficient for similarity searches and clustering and retrieval, where identifying patterns or groupings in data is critical. Embedding models are generally smaller and more specialized for specific tasks compared to LLMs. Let's compare embedding models to LLMs like GPT-4, any of its variety of versions. These take things to another level. Now, where they could probably generate embeddings as part of their broader functionality, they're designed for more complex tasks. They don't understand context as well as they can generate responses, make predictions, and synthesize information across large bodies of knowledge. LLMs are trained on vast data sets and can perform a wide variety of tasks, from answering questions to writing code. So an easy way to think about this is embedding models are used to convert raw data into vectors that can be stored and retrieved efficiently. Cool, it's a data storage, retrieval, search kind of problem. LLMs, on the other hand, can generate embeddings, but are primarily used to process text and generate text. They kind of leverage this understanding of language to perform these complex tasks. They found the patterns in the way we speak. Embeddings are just about kind of converting to a pattern. So where do these models fit into kind of the overall AI ecosystem? Well, embedding models typically come into play when you need to represent data in a form, similarity search, or clustering. Recommendation systems, product features, LLMs are good when you need to interpret, generate, or manipulate that text. And you can kind of pair the two together in a chatbot system where, embeddings of previous conversations, you might be able to push into a vector database. And then when a user asks a new question, the system can retrieve the relevant embeddings and pass along this additional context to the LLM. Generate a more personalized response. If you've seen the memory feature of ChatGPT, that's exactly what this thing is doing. That's literally what it's doing. It's taking snippets of previous conversation to store additional context and figuring out what's relevant to the conversation at hand and injecting it. So in short, both embedding models and LLMs are kind of critical to the AI space. One's good at generating and synthesizing information. The other's good at representing that complex information in a way that can be retrieved and used. But they operate at different stages for different objectives, right? They kind of work together but do different things. Let's get back to the vector DB thing, right? We talked a bit about vector search and how it differs from traditional lexical search. Let's dive into the vector DB where these embeddings live. So you can use embeddings standalone. You don't have to put them into a database. But if you want to have any chance of building a production system, you're going to put them into a database. So vector DB is a specialized store for querying high-dimensional vectors efficiently, just like database. This relational database is a store for querying normalized text. So while traditional databases and search engines aren't optimized for the task, but there's more specialized vector databases out there. Vector databases like Pinecone, Weaviate, and FAISS from Facebook. FASIS, I don't know how to actually pronounce that. All these links will be in the description. Don't you worry. Go find it there. But they're all built from the ground up to manage embeddings. It's an advanced indexing techniques used such as an approximate nearest neighbor, ANN, perform similarity searches quickly, even over billions of vectors. Just like a graph database is good at finding relationships. Sure, a relational database could, but not at the scale that graph databases can. So to put it simply, ANN algorithms are like finding the closest book in a huge library based on a similarity in meaning, not just the exact title. They help make searching in higher dimensional space efficient and scalable. So let's say we're going to revisit our image search engine example from earlier. Users upload a photo and the system returns similar images. Each image is represented by an embedding, and when a user submits a query, the system generates an embedding for the image and searches the vector DB for the closest match. The efficiency of this search is crucial for a good user experience. Latency, killer of user experiences. And that's where a vector DB excels. They're really good at handling this challenge of scaling and updating these embeddings at volume. When new data comes in or models are retrained, embeddings can change. Vector DBs are designed to handle this dynamic data, supporting real-time updates without significant performance degradation. So there is a space for them and there's utility for them, but I wouldn't say they're the only tool you should be having in your AI engineered systems, right? Even if it's another bolt-on LLM. That still doesn't count. Security and scalability are important when we're deploying large systems across multiple nodes, distributing data. You got to worry about encryption, access control. It's all baked into the vector DBs. All there for us. Don't have to worry about it, which is kind of nice. So for AI engineers, leveraging vector DBs means you can build applications that are not only intelligent, performant, and scalable. Piece of the application. I would still say you want to think about lexical search and some of the other stuff layered in there. But it allows you to focus on delivering value without getting bogged down in the complexities of vector DB storage and retrieval. So I've mentioned graph databases, I think at least a couple of times at this stage. So let's talk about how they also fit into the AI engineer's toolbox as a foundational technology. Like I said earlier as well, they're not new. 10 years ago, I was building software with them, but they do complement a vector database when building AI systems. Graph databases are excellent at modeling those complex relationships between entities. Neo4j, for example, data is stored as nodes connected by a relationship, making it easy to represent a social network or social connections, recommendation systems, knowledge graphs. Just like having a composite stack, when we integrate graph databases with vector databases, we enable our AI systems to consider both the semantic and relational context, right? So we've got semantic, we've got lexical, we've got relational context. So we layer this stuff together, we start to build more complex machines that can do more for us. More complex product, I guess. For instance, suppose you're building a recommendation system. You can use embeddings to find similar products based on features and user preferences, handled by the vector DB, and then use a graph database to understand the relationship like co-purchasing patterns or social influences. It's not magic. You don't just plunk things in and ask a few questions and out pops the result, right? There's still a lot of work to be done here, but there's nuance. There's deeper levels of nuance to unlock more value. So by combining these technologies, you build systems that not only find similar items, but also understand how the items relate to each other in a broader context. It's also worth noting that while vector search handles similarity, graph databases handle relationships. Together they provide a pretty powerful toolkit for building intelligent systems. This is why you see a lot of AI stuff out there talking about graph databases and vector databases coming together. It's just a marriage of existing technologies to unlock value. Nothing new or fancy. Tools like Neo4j have evolved to integrate with better with AI workflows. They offer plugins and integrations that allow you to perform graph queries right alongside vector similarity searches. So Elasticsearch, the traditional lexical, is starting to play in the vector space. The graph searches are starting to play in the vector space. It's all flowing together. It's all part of one really nice, fluid AI engineering toolbox. The integration of these technologies represent a convergence of different data paradigms. Like I was saying, structured data, unstructured data, relational data, all the ways that we model things in the world coming together in a fluid space. I love it. This allows our systems to be more robust and versatile. And I've really tried to avoid the term RAG, or retrieval augmented generation, when discussing this. It's hard. I want to specifically not anchor us to that. In the next episode, I'll be diving way more into how, all of these technologies come together in RAG type systems and why, what's where, and why graphs and RAG are kind of the hypey thing at the moment. But anyway, it's all just layers of technology, old stuff working together, making things more fluid. It's just the progression of the industry. I used to have to write make files to build software. Now I just click a button called build. Progress, people. It's good stuff. So let's bring it all together. Let's look at a few examples without going into too much detail. Remember, I want to kind of save that for next episode. How embeddings, vector DBs, graph DBs all come together to build more intelligent systems. One idea is recommendation systems, vector search, graph relationship, can enhance personalization. For example, a streaming service can use embeddings to find similar movies based on user preferences, and then use graph relationships to understand viewing patterns among similar users, leading to better recommendations. Or social networks are another area that really shines here. Platforms can represent users and their interactions in a graph, while embeddings can capture user preferences and behaviors. And then when suggesting new connections or content, the system can consider both the semantic similarity and the relational proximity in the social graph. Okay, cool. Maybe that's a bit how Facebook works. Let's look at another one. Fraud detection. Embeddings can represent transactional patterns, and graph databases can model relationships between accounts, transactions, and entities. This approach helps in identifying not just suspicious transactions, but also networks of fraudulent activity. And one more while we're at it. Supply chain companies can model their entire supply chain network in graph databases. Embeddings can represent various attributes of suppliers, product, and logistics. Then when disruptions occur, an AI system could quickly identify alternative routes or suppliers by considering both the relational and semantic aspects of the information. All about data, people. But in all these cases, the combination of embeddings with vector databases and graph databases enable AI systems to understand and respond to user situations in more meaningful ways. We're building on the advancement in technologies in other ways to create more fluid systems, really. So for AI engineers, mastering these technologies allows you to build systems that are greater than the sum of their parts. By leveraging the strength of each, semantic understanding from embeddings, efficient retrieval from vector databases, and relational context from graph databases, you can create applications that are intelligent, responsive, and scalable. Whether you're working on search, recommendations, chatbot, or complex decision-making apps, integrating these technologies opens up new possibilities and enhances the capability of your AI solutions. What's the big takeaway from today's episode? Well, that embeddings, vector databases, and graph databases form the backbone of many modern AI systems. They enable these systems to understand context, find similarity, and comprehend relationships, while providing personalized and meaningful experiences to users. We've explored how vector search represents a paradigm shift from traditional lexical search, enhancing the ability to understand the user's intent and deliver more relevant results. We also discussed how graph databases add a layer of relational understanding, enriching AI applications by modeling complex relationships. If you're curious about how to start experimenting with vector databases or embeddings, because they're the hot topic, right? You might want to try a free tool like Pinecone. Not promoting it, just putting it out there. It's the one that came to mind. Concepts in action. And to dig even deeper, feel free to reach out. Questions, specific use cases you're interested in, or tools, happy to engage, please. Because as AI engineers, mastering these techniques isn't just a nice to have. Technologies, not just techniques. It's essential for building scalable, intelligent AI products that allow you to transform raw data into actionable insights, powering features that make applications stand out in a true value-add way. As I've alluded to throughout the episode, in our next episode, we'll be looking at Retrieval Augmented Generation, or RAG for short, powering contextualized and personalized AI. We'll explore how RAG systems combine the strength of generative AI with retrieval mechanisms to provide more personalized, context-aware responses. So whether you're looking to build advanced AI chatbots or enhance your customer service tools, this episode's one you're not going to want to miss. And as a side note, I'm going to be taking a short break of about a month. Afterwards, I look forward to delving into the RAG systems with you upon my return. So thank you for joining me on this deep dive into vector databases and embeddings and Neo4j. So if you've enjoyed today's episode, please subscribe, leave me a comment, thumbs up, and until next time, keep experimenting and stay curious.